All right, so again, in section 3.1, you learned about cofactor expansion. And cofactor expansions can be used to compute the determinant of a matrix by expanding along any row or any column, and it works for any size of matrix too. So it's a very general approach. But the problem is it is computationally difficult to compute the determinant using cofactor expansion if, for instance, you have a large matrix. And we actually learned in the numerical note at the end of section 3.1 that if you had to compute a determinant for a matrix that's has 25 rows and 25 columns, and let's say it's a dense matrix, meaning that very few zeros in the matrix. Using a computer, it would take more than 500,000 years to compute that determinant using cofactor expansion. And so obviously we need to find another way that we can more easily compute determinants. And that's where section 3.2 comes in. Section 3.2 deals with properties of determinants. And there are three properties that are outlined here. Okay, let me see here. Let me highlight it. So first of all, of course, for a determinant, you let A be a square matrix. And you don't have to copy these rules down. They're in your book. But we'll be looking at them a little more closely. But the three rules are the determinant rules. And, the first rule says if a multiple of one row is added to another row to produce a new matrix B, or a matrix that's row equivalent B, then the determinants of A and B are the same. Rule B says if you have a matrix A and you interchange the rows to produce a new matrix B, or I should say a row equivalent matrix B, then the determinant of B will equal negative times the determinant of A. And finally, if one row of A is multiplied by K to produce matrix B, then determinant of B equals K times the determinant of A. So these three rules are going to help us tremendously in computing determinants of matrices. And what I'd like you to do, I mean, sure, you're seeing the rules, they're stated there, but I want to go through a little example with you to help you feel comfortable with why the rules are true, to give you an intuitive feel. So on that note, let me go ahead and bring up now some notes for the class. Are there any questions so far? Okay, let me bring up those notes. Yeah, this is what. Okay, so what we're going to do is let me give you a moment to copy this example down. Let's give you a moment here. Okay, so here what we want to do is we want to discuss the three properties that you just saw in the textbook of the determinants, three properties of determinants with an example. Okay, because I think the example will help you appreciate the rules the three rules for determinants, computing determinants. May I go to the next page? Does everybody have this copied okay? Okay, Abby's good. Good. All right, Benjamin's good. Namath's good. Okay, then let's move forward here. Okay, so what I have is I have this matrix A here, and I just picked I just thought of this 2 by 2 matrix up in my head. You know, the matrix A is in this case 1, -2, 5, and 7. So the first property in section 3.2, the very first property says that if a multiple of one row of A is added to another row to produce a matrix B, then the determinant of B equals the determinant of A. Okay, well let's test that rule out. Let's test that rule out. So what I'm going to do to the matrix A is I'm going to take -5 times the first row and add that to the second row and replace the second row by that result. Okay. All right, so I just picked that row operation. And I guess it's because I wanted to get a 0 here. But it doesn't really matter. You know, this type of row operation. But what I'm trying to say is the row operation I'm doing is of the type A in theorem 3 from section 3.2. I'm taking a multiple of one row and adding it to another row. I just decided to pick -5 times row 1 and add it to row 2. And this is the matrix B that results. So what I want to do is I want to compute the determinant of A and the determinant of B and see how they compare. Well, these are 2 by 2 matrices. It's very easy to compute the determinants. The determinant of A will turn out to be 17, and the determinant of B will also turn out to be 17. So therefore, the determinant of A equals the determinant of B. Just like theorem 3, rule A says in section 3.2. Okay. All right. Are there any questions on that? How many like rule A? How many think this is pretty cool? Or interesting? Okay, Eleanor likes it. All right. Hung likes it. Good, good. All right, name as well. Wonderful, wonderful. Excellent, Abby. All right, well, let's go ahead and go to, let's examine the second rule. So I'll go to the next page, if I may. So we looked at property A of theorem 3. Now let's look at property B of theorem 3. Property B says if two rows of the matrix A are interchanged to produce a matrix B, then the determinant of B equals negative the determinant of A. So again, here I am with that same matrix A, and I'm going to interchange the rows 1 and 2 to produce this matrix B. And now I'm going to compute the determinant of A in B. The determinant of A is 17. The determinant of B is negative 17. Therefore, the determinant of B is equal to negative determinant of A. And this confirms the rule B from Theorem 3 in section 3.2. So sometimes it helps to kind of, when you're given a lot of like information, like in theorems and things, I find it helpful to think of an example to kind of a concrete example to confirm the theorem, and then I feel better about the theorem. How many kind of feel that way? Okay, Benjamin, thank you, everybody. Got a lot of people here. That's good. I'm glad to hear. Thank you, everyone. Are there any questions on this rule? All right. Well, then let's go to the last rule. Rule C. Property C. So property C, looking at Theorem 3, property C is that if one row of A, if one row of the matrix A is multiplied by K to produce the matrix B, then the determinant of B equals K times the determinant of A. Okay, so here I am with that same matrix A, and I choose, just out of the blue, I choose to multiply the first row by 4. So the first row, which was 1, negative 2, now becomes 4, negative 8. And here's my matrix B. The determinant of A, of course, is 17. And the determinant of B is going to be equal to 68. Well, that means that the determinant of B is 4 times the determinant of A. 4 was the K value. And so that confirms Rule C. Are there any questions at all? All right. Well, now that we feel comfortable with these properties, with this theorem, and these 3 properties of determinants, how are they going to be useful to us? How are they going to be useful? Well, our original goal was to find a better way to compute determinants, or an easier way, I should say, of computing determinants. We still need to do cofactor expansion, but we could maybe make the cofactor expansion a lot easier. And so let's look at an example here. Okay, here's this matrix A. It's a 4 by 4 matrix. How many of you would want to do that, compute the determinant of that matrix using cofactor expansion, like just straight cofactor expansion? How many would like an easier way? Okay, Benjamin's right. There aren't a lot of zeros. It would be hard. Haley says not really. And yeah, and Eleanor wants an easier way too. Well, here's an easier way. What we're going to do is we're going to do row reduction on the matrix A. We're going to get it into echelon form. And as we do this, we're going to simultaneously modify our determinant of the matrix A as we go along. You'll see what I mean. You'll see what I mean. All right, let me give you a moment to copy that. Okay, so let's go ahead and reduce this matrix A to echelon form and simultaneously look at the determinant. So, okay, here we are, the next page. So what I did was, of course, this is the matrix A. I just rewrote it here. And obviously, this matrix A, we could use straight cofactor expansion on it to compute the determinant, but it would take time. There aren't, as Haley pointed out, there are very few zeros in that matrix. So it would take time to use cofactor expansion. So let's see here. Let's see. Okay, let me just look here for a moment. All right, so what I decided to do was, if you look at the first row, I'm going to multiply the first row by a half and replace then the first row with that result. In other words, I'm using theorem 3C. I'm using property C of theorem 3 in section 3.2. Okay, I'm multiplying the I'm multiplying the first row of the matrix by a half, okay, to produce this new matrix here. But then the determinant of A would have to be 2 times the determinant of this matrix. Think of it like this. Think of it like this, okay? Let's say, okay, I got this matrix here in the circle, and I'm going to put the circle here. Here's the matrix, okay? Is that matrix equal to 1/2? So this isn't very, hold on. I got to be a little bit careful here. Oh, I can do better than that. I have to model good math technique here. So this is going to be the determinant of B. So is the determinant of A times 1/2 equal to the determinant of B by rule C of theorem 3. And you may want to have those rules, you could have them, I'm trying to think, you can have them like on your ebook, you can have them on your screen, or I don't know if you can, divide your screen up into two, like a left and a right. How many of you do that? Maybe do you have like, what's it called, a split screen? Does anybody do a split screen here? Okay, Hong does and Catherine does. Okay, good. So what I'm trying to say is, you notice how I essentially, it looks almost like I factored a 2 out. It looks like I took this first row here, and it looks like I factored a 2 out. But effectively, what I'm doing is I'm utilizing theorem 3C, because the fact that I multiplied this first row by a half, the half is my K, to produce then this new row in my new matrix B, that means that the determinant of B has to equal 1/2 times the determinant of A. And therefore, the determinant of A equals 2 times the determinant of B. So I'm trying to justify this step. Is that okay, what I just explained there? Are there any questions on that? Okay, Shravani's good. All right. Who's comfortable so far up to here? Okay, Naima is good. All right, Livia and Abby and Ben. All right, wonderful. Well then let's continue here. So I kind of call this step like a factoring step, even though it isn't really factoring. It kind of looks like it's factoring, right? So a scaling step is effectively like a factoring step when you compute your determinant using the row operations. Now what I want to do is I want to take the 1 here and use it as a pivot to produce zeros in these 3 places in the first column, below the 1 in the first column. So I'm going to do three row, I'm going to say it the right way. I want to do 3 row replacements. I want to take -3 times row 1, add it to row 2. I want to take 3 times row 1 and add it to row 3. And I want to take -1 times row 4, sorry, -1 times row 1 and add it to row 4. So essentially, I am applying then theorem 3 part A. And I did it 3 times. But what do you notice about the determinant? Did the determinant change? I mean, it stayed the same? That's right. That's right, Hung. This determinant here is the same as this determinant here. And that's because row replacement operations do not change the value of the determinant by theorem 3a. Now look at what's happening here. What do we like that's happening here when we're doing these row operations? What good thing is happening? What are we getting here? Ah, good. We're getting zeros. We're getting zeros. We like zeros, okay? And there's no, there's really very little cost, right? The things we're doing here, these properties that we're applying in computing the determinant, like for are easy, okay? Okay, let's continue. Now what I'm going to do is I'm going to use the 3 here as a pivot to produce a 0 where the negative 12 is. So I'm trying to get the matrix in echelon form. So I take 4 times row 2 and add it to row 3. And then here's my new matrix. And again, the determinant doesn't change. Okay, and so far, we have even more zeros. Okay, the next step, of course, is I want to get this matrix in echelon form. So, but I wanted to kind of, in this example, demonstrate the 3 properties. So what I decided to do was to take the third row and the 4th row here and interchange those rows. So now that's theorem 3b, a row interchange. But when I do a row interchange, what is introduced? What is introduced in the for the determinant? A negative 1. That's right, Benjamin. Okay. So, okay, well, that's no problem. That's no problem. We can deal with that. That's easy. So you see now all 3 properties being applied towards computing this determinant. Are the properties easy to apply, class? Are they pretty easy to apply? Is it easier than cofactor expansion? I think Hung thinks so. So far, is this easier than doing cofactor expansion? Okay, thank you, Eleni. Much easier. Much easier. Ariana agrees. Okay. All right. All right. Well, we're almost done. We're almost done. So the final step, of course, is I want to, well, the final step is I want to use the negative 3 as a pivot to produce a 0 where the negative 6 is. So I'm going to take negative 2 times the 3rd row and add it to the 4th row. But to do that, I have to go to the next page. Is everybody, may I go to the next page? Okay, let's do it. Thank you, everyone. Let's do it. So, okay. I did that row operation. Negative 2 times the 3rd row, added it to the 4th row. Again, that's applying theorem 3a 1 time. So now the matrix is in triangular form. And now cofactor expansion is easy, right? Okay, so triangular form means below the diagonal we have all zeros. Well, you can have also triangular form. Is this lower or upper triangular form, what you have here? Is this upper triangular or lower triangular form? Good, upper triangular form, that's right. So then, that's right, Eleanor Hung, that's absolutely right. So then cofactor expansion is just then equivalent to finding the product of the diagonal entries. For cofactor expansion, what column would you expand down? The first column. Okay, very good. And so the 2 times the -1, that resulted from the properties of determinants that we applied. And then the 1 times 3 times -3 times -2 just equals negative. That's just the product of the pivots on the diagonal. Okay, so in this form here, we call it form U. Okay, and we get -36. So if it's easy for us to do, hey, with a little programming on a computer, it would be easy for a computer to do. All right, are there any questions? All right, so we're gonna do a little something more with this example. That's why I have the arrow here. I mean, we're done computing the determinant, but I'm going to show you something. We're going to do a little something more with this example, but I want to just bring up the numerical note real quick in your book. I want to bring up that numerical note. Hold on here. So how efficient is this, doing determinants this way using the properties? By the second rule here, okay, by the second rule, hold on, let me make that highlighted. It can be shown that evaluation of a n by n determinant using row operations requires about 2n cubed divided by 3 arithmetic operations. Any modern microcomputer can calculate a 25 by 25 determinant in a fraction of a second. Okay, not 500,000 years, a fraction of a second, using row operations to help you. How many think that's absolutely fascinating? Yeah, Benjamin likes it. Abby and Ariana like it, and Catherine and Hung, and hold on, a lot of people here. Some more people. Naima, Olivia, absolutely. Well, all right. So so I want to show you a second way to compute this determinant, the determinant of the example that we just looked at, using using the row operations. Okay. So okay, let's continue here. Now, let's compute the determinant a second way. Okay, a second way. Hold on. In other words, this second way we're not going to involve any factoring. In other words, we're not going to be scaling any of the rows. We're not going to be multiplying any of the rows by a scalar. We're only going to do row replacements and row interchanges to compute the determinant. And in fact, any matrix A can be, the determinant of any matrix A can be found using only row replacements and row interchanges. The scaling is not necessary. You can do it, but it isn't like needed. Row replacements and row interchanges are needed. If you're to, I mean, in other words, what I'm trying to say is you're trying to reduce the matrix A in echelon form, okay, in this upper echelon form. So you're going to need to do row replacements and row interchanges. However, multiplying a row by a scalar is optional. And so I just wanted you to see this. So here's the matrix A again. Okay, and this time, hold on here. Let me just one moment. This time, what I do is I interchange rows 1 and 4, and then that produces the -1. And actually, I can put -1 to the first power even, if I want. Okay. But it's -1. So that's an application then of the, hold on here, theorem 3, that is the theorem 3b, the second rule. All right, and then what I do is I want to produce zeros. I want to get zeros in these 3 spots in the first column below the 1. So I use the 1 as a pivot to produce, to help me get zeros. So then the row operations here, the row replacement operations are right here that I'm doing. And row replacement operations don't change the value of the determinant. Okay, so this determinant here is equal to this determinant. All right, are there any questions up to here? All right, well then let's continue. So now what I want to do is I want to get a 0 where the -12 is. So I'll use the 3 above as a pivot, and I'll multiply the second row by 4 and add it to the third row. Again, that is just a row replacement operation. So the value of the determinant does not change. And as we do every one of these row operations, the matrix is looking nicer and nicer. And why is that? Why is the matrix looking nicer and nicer? What are we seeing more of in the matrix? We're seeing more zeros. Good. Good, Samantha. Good, Ariana. Very good. Very good. All right. Well, okay. So we know that we need to get we want to get a 0 where in this spot here, in this spot. But the 6 is a smaller number. It's easier, being that we're doing these row operations manually, it's easier to use the to interchange rows 3 and 4 and use the 6 as a pivot. Now, in fact, sorry, one moment. Using what's called partial pivoting, they talk about that way back in section, hold on here, I'm going to find the page here. Yeah, way back in section 1.2, there's a numerical note at the bottom of page 17. It comes right after they're done with example 3. But partial pivoting is where you use the bigger number as a pivot. So a computer would actually use the 21 as a pivot to produce a 0 where the 6 is. But as humans, we're gonna not do that. We're gonna interchange, and I guess I forgot to put the instruction down here. I'll put it down right now. We're gonna take row 3 and row 4 and do a row interchange. Now, did that produce something here? Did that produce, did that produce something that we have not seen yet? Something new? Another -1. That's right. That's right. Right here. Because anytime, thank you, Hung, anytime you do a row interchange, you introduce another -1 factor. All right, and now what we're going to do is we're going to get a 0 where the 21 is, using the 6 as a pivot. So, well, we got to multiply the second row by what? We got to multiply the second row by a fraction and add that to the fourth row. Okay, what fraction would we multiply the, I'm sorry, we got to take the third row, multiply it by a fraction, and add it to the fourth row. What fraction would that be? Good, good, very good, Hung. -21/6. So I'll go to the next page if I may. Okay, I take then -21/6 times the third row and add it to the fourth row. And now my matrix is in upper triangular form. It's in echelon form. I have triangle zeros below the diagonal. And so the determinant of A then is just going to equal -1 to the second power. The power 2 gives the number of row interchanges that we used. And then the rest of the determinant, well, I mean, we need to multiply -1 squared by the product of the pivots in U. These are your pivot numbers right here along the diagonal. And this is traditionally how a computer will compute a determinant. Okay, most computer programs don't use scaling of rows. They do simply row replacements and row interchanges for computing the determinants. In other words, the computer programs will row reduce the matrix into upper triangular form using simply row interchanges and row replacements. And there's a formula on page 173 in the text for computing the determinant of A. That's used by most computer programs. I'll show you the formula in a minute, but that formula is really just, it's really exactly like what we did here. So I wanted to compute the determinant this second way because that's how computers do it. But let me give you a moment to catch up here. All right. May I go ahead and move to the textbook? Does everybody have this copied okay? Does anyone need more time or you're good? All right, how about a few thumbs up then? And I'll move forward. Okay, good. Hung's good and Abby's good. All right, Samantha's good. Lewis and Marvelous, wonderful. All right, well let me go ahead here and show you the formula in the book here. Hold on. Okay, so really, what they're talking about here is what we just talked about. Okay, let me make sure. Hold on, everything's okay. Good. Nafani, yes.
Can you hear me?
I can hear you, Nafani.
Yeah, going back to the last problem we just solved in the determinant of A.
Yes.
After interchanging the first row and the fourth row,
Hang on. Let me get it here. One moment. We'll come back. One moment. One moment.
Sure.
Okay, one moment here. One moment here. Let me go. So it was the second way, right? Second
Yes,
way?
yes, Professor.
Okay. After interchanging the first and fourth row?
Yes, Professor.
Okay.
Okay, okay. All right, I see now. The error is mine. On my, what I copied was I had a negative sign on the first entry. On
Oh,
the
okay.
I had the -1, so I was wondering where did the minus sign go. It was my mistake.
Oh, no problem. Okay.
Yeah, sorry about that.
That's all right. That's all right. All right. All right. Well, let's see here. So, okay. So the book in section 3.2 here, I'm trying to not have it highlight everything in the world here, but yeah. So let me check that book, make sure it's showing. Okay, the book's showing all right. Let me know, class, if that book disappears on you, okay? Maybe give me a few, just let me know, you know. All right. So if a square matrix A has been reduced to echelon form U by row replacements and row interchanges, this is always possible, then there is a nice formula for computing the determinant of A. The determinant of A is simply -1 to the rth power, where, you know, that's if you have R interchanges, times the product of the pivots in that echelon matrix U. We just saw that in the example we did. Our determinant of A was computed by taking -1 squared, because we used 2 row interchanges, and then just multiplying the product of the pivots in that matrix U. Okay, hold on here. Yeah, in echelon form. Now, why is why, like, so you know that, well, if A is not invertible, the determinant of A equals 0. That's a property of determinants. If A is a non-invertible matrix, its determinant of A equals 0. But of course, the more interesting matrices are the ones where the determinant of A, you know, when A is invertible. Okay, so how many kind of think this is pretty cool, this little formula here? That formula 1 there. Yeah, definitely easier than cofactor expansion for a computer to do. Okay, definitely easier. And the book, again, comments in the numerical note, well, I'll just say a square matrix is invertible if and only if the determinant of A is not equal to 0. Okay, just think about if you intuitively want to feel for that, think about the formula for a inverse of a 2 by 2 matrix. In that formula, in front of the, like you have as part of the formula, you have 1 over the determinant of A for a 2 by 2 matrix. And so that determinant of A, if that's 0, then you'd have 1 over 0 and you'd have a non-invertible matrix. I mean, if you want to kind of think of a little example to help you feel comfortable with that. But here, they make the comment that I can take this off here, most computer programs that compute the determinant of A for a general matrix use the formula, hold on here, 1 above. And the formula 1 above is this formula here. And it's important to recognize that, because it's going to be helpful for your second MATLAB assignment. I'm going to be I'll be posting and talking about your second MATLAB assignment next week. But of course, in order to really talk about it, you have to understand properties of determinants. Okay, so are there any questions on that? All right, let me stop the recording.